Hey, Reza, I see the presenter's view, so you may want to flip them. There we go.
I'll pop a link to the Google Doc into the chat.
Sounds good. All right, we've got 20 presenters, and I'm just kind of keeping an eye on things to see whether we continue to get one or two more, and then I think let's wait for about 30 seconds and see if we can get going then. Just for folks who are here, remember that we do have the Google Doc. And we definitely want, folks have not been using them as much as I had hoped, but we definitely want comments and suggestions and criticisms and, you know, sort of what the heck are you guys thinking kind of comments are perfectly welcome. So please use that document for those sorts of things. We will review those on a regular basis. We will continue to keep up with them after the workshop. So it's a great idea for being able to communicate with us about this subject. Okay, Andrea, you are now a co-host. All right, why don't we go ahead and get going? I think we're pretty stable now at this point with the number of participants. So we're going to be talking about some communications trades that we've got going on. Dave did a really good job of talking about sort of the baseline concept yesterday and how that ripples into how much data we can get down. But there are a number of aspects of this that this is one of the prime areas for optimization on the concept. And so you know, we definitely want to be keeping up with all of that. And Reza is going to share, I think, the story of the trades and how those might ripple into things going forward. So with that, Reza, why don't you go ahead? Okay, Reza, are you there? I see you're unmuted, but we're not hearing you.
And we're seeing your mouse.
And I see his video. So Reza, are you hearing us at all? Okay. All right, well, that helps diagnose the problem. Interesting that this would happen during a communications talk.
Well, we had a reliability issue yesterday with the reliability presentation.
That's right.
So.
We are simply demonstrating that the information rate's going to be very low.
Wait, does this mean we're going to get hit by a blast of cosmic waves raised during the CGR portion?
Are we testing our fault tolerance right now? And recovery methods?
That's right.
Okay, can you hear me now?
Yes.
Yes. All right, all hope is not lost. Okay, so thank you, Jim. My name is Reza Ashtari. I worked with Dave Copeland, who's the telecom systems lead on this interstellar probe trade study. And I just want to say thank you to everybody who's at the workshop and attending this in one way, shape, or form or another. You've obviously committed your life and pursuit towards a noble pursuit, so I commend you on that, and I'm sure we'd be friends. So we'll go ahead and start. Okay, so just going over the NASA guidelines that I'm sure Jim and a few other people have mentioned so far. We were flowed down for our interstellar probe mission study, a few guidelines from NASA, and a few of those were have a system design that would be ready for launch no later than 2030. So that really implies having a lot of high TRL level technologies in our notional system design. Try to make the comm system operable from 1,000 AU, and we somewhat gave ourselves the goal of trying to reach 500 bits per second as a nominal goal. Power, we plan on having 2 RTGs on our notional system design, and at end of life, they would drain down about half the output power, so from 600 to 300 watts. and I'll talk about how that influences everything that we chose. And in terms of longevity, we are really limited in all of the technologies, whether it be momentum wheels or secondary pointing or something like that. We really had to take careful consideration as to what we included as part of our design. So I'll kind of dig deeper into those. So diving into the notional system design, you can see the block diagram here to the right. So we have an HGA, a high gain antenna, medium gain antenna, and then we have two low gain antennas that are really primarily for early operations. You can see them diagrammed out on the picture of the spacecraft to the left. And then we list out everything that we have. It's designed in a dual redundancy type of effort. The only thing that isn't redundant is that CXS switch that we have that everything feeds through, but that has a very low fail rate. And I'm not sure if the risk and reliability folks will dive into how or the percentages of reliability for each of these, but we have the system designed for some level of redundancy at least. Kind of diving into how we gauge the diameter of our high gain antenna and whatnot. It's important to point out that, no pun intended, that our pointing error was our main limitation in our design. So the rest of the design is really limited by this 0.2 degree pointing error that is really a legacy learned limitation from New Horizons, which I believe had roughly a 0.3 degree pointing error. And it's also important to point out that the spacecraft needs to point while spinning. So a lot of people tend to draw comparisons to Voyager, which was a 3-axis stabilized spacecraft, but really we're essentially like, from a communication standpoint, we're a lot like New Horizons, but with a bigger dish and with slightly improved pointing. So if you look at the trade here, the y-axis shows data rate using 4 arrayed 34-meter dishes, and that's supposedly the equivalent to a 70-meter dish. And there's been talk off and on via the DSN whether the 70-meter dishes are going to be discontinued or not, and replaced by these beam waveguide 34 meters. So taking the link capability out to 1000 AU, you can see that using DSN only, you can only get in the tens of 30s of bits per second, which is pretty cruddy, but we'll talk about how we're going to improve that as well. The black line shows, or the black curve shows our X-band downlink performance using DSN, and blue shows Ka-band. And again, this is limited to 0.2 degree pointing error. If we were able to improve that pointing error, we could afford to point tighter beams and we could get away with Ka-band. But for now, that 0.2 degree limitation really limits what frequency of operation we can choose for our comm system. And the vertical line here shows how we're also limited by the diameter of the fairing of launch vehicles. So we're kind of limited in expanding our dish size out to only 5 meters. I remember yesterday, I believe it was Alan pointed out, why don't you maximize your dish size so that you can get away with an even better link? Well, to your point, a 7-meter dish would actually be the optimal size. But for risk and reliability reasons, we wanted to not consider a deployable antenna and stick with just a rigid or non-deployable reflector that would fit within our fairing. So kind of flipping this 3-dimensional trade study on its head between diameter, data rate, and pointing error, if we were to keep that maximum aperture size that we get away with, how much would we need to improve our pointing error in order to achieve Ka-band? And I wouldn't dig too deep into this because I'll go over some Ka band options later on, and this 0.08 degrees is more so just for a demonstration to show that really we can do Ka band if we can implement some sort of pointing capability that improves upon our current capability of only 0.2 degrees. So we need to get to at least 0.08 if we're going to keep that maximum size of aperture. So how does this compare to some previous legacy deep space missions? So in terms of performance, yeah, you can look at the antenna diameter and the transmit power. Those are going to be the key differentiators as to what kind of data rates we're able to achieve. And for more so an apples to apples comparison purpose, we've kept everything in this link model transmitting down to a 70-meter DSN station. And for our nominal design, as I mentioned, we have a fairing diameter limited 5-meter size dish, and that's being fed 52 watts of RF transmit power, and that's based on operating on a single RTG at end of life, and we're assuming we would get 90 watts of DC from that RTG dedicated to telecommunications, and with our TWTA, we'd be able to produce from that 90 watts roughly about 52 watts of RF transmit power. We assume regenerative ranging, a pretty modest 20-degree elevation for all of our link models. So we're really communicating through a good bit of atmosphere at a pretty low point. And we also assume a 3 dB margin. And as I mentioned before, we're operating at what we hope to be a 0.2 degree pointing error. So that was at Jupiter. I forgot to mention that. So that's why all the data rates are pretty high, but that's supposed to provide the apples to apples comparison. If we move on to the mission distances, then you can see really how difficult this link becomes. The bottom row, we've defined our link difficulty in terms of megabits megabits per second of data rate times AU squared. And doing that, you can really see that quantitatively, we have over 100 times more difficult of a link to accomplish here than at the Voyager missions, at least with them achieving their standard telemetry of 160 bits per second. And I would also like to point out that although we have a 500 bits per second goal, roughly, even if we stay at the DSN using a 70-meter, our 50-year end of life at approximately 375 AU, we're only going to get about 254 bits per second. And at 1,000 AU, it's an incredibly cruddy 35 bits per second. So I'm going to go into kind of the knobs that we can turn to improve our data rate and downlink performance. So the first one of the knobs that we're going to turn is our ground stations and our aperture sizes. So primarily, most missions, they rely on the DSN for coverage. And as you saw in the previous figure, we really can't reach our goals relying solely on the DSN. And so some other national radio astronomy facilities ended up having X-band operation that we could possibly work with. And their performances were provided on their own websites, but they're typically given in astronomers' units. So there's a pretty simple conversion that you can do to transmit or to convert their gain and sensitivity values into our engineering or satellite communications gain and sensitivity values. I would also like to mention that we considered a few other radio astronomy facilities. Arecibo was brought up, but because of their limited field of view, it wasn't considered because you can only get about 2 to 3 hours per pass or per contact. The square kilometer array was considered as well, but after speaking to a few people on the interplanetary network development organization, they mentioned that the SKA is very likely to abandon their X-band operations. So we were really left with the Green Bank telescope and the next generation VLA. And I would also like to point out that yesterday, I believe it was Bill Kurth mentioned, it's worth, especially for Voyager nowadays, they're arraying into 434 meter dishes plus a 70 meter. And that's roughly equivalent to the performance that you're going to see from the Green Bank telescope, although it's slightly less, because the Green Bank telescope does have an active surface where it moves the panels on the surface of its big dish to improve its overall efficiency. And that really ends up helping it out. So in terms of the performance carrying out from launch to 1000 AU, here's kind of what we can expect. And you can see that really the most drastic leap in performance is provided when we can move away from the DSN and more towards the NGVLA. Now, I would like to point out also that we're rather optimistic in assuming that we're using all 244 18-meter dishes of the NGVLA for the performance that's shown here. But this is just a preliminary look as well. Another takeaway is that also we're pretty good on using DSN coverage, at least up to around 200 AU-ish. And so that really buys us a lot of years in terms of time before we need to switch over. And yeah, in terms of uplink, how that would look is we would stay on DSN facilities primarily, and tradition has been for past deep space missions like New Horizons and whatnot, we've kept our command uncoded. And for these purposes, we're going to have to improve our signal noise ratios a little bit when trying to uplink, especially up to 1000 AU. So we'd really consider some type of additional coding scheme. So here we've assumed LDPC coding on our, or dual parity coding on our uplink. So that helps us in terms of extending the range of that as well. This is also assuming an 80 kilowatt transmitter from the 70 meter, from all the dishes, as these are planned to be installed in the DSN's facilities over the next few years. So that upgrade is already, I believe, installed in at least one of the DSS dishes, and it should be a sweeping installment amongst all of them. So what does that buy us? This was the performance that we saw before. And you can see the maximum data rate that we were able to achieve before. It was pretty cruddy when using only the DSN, or at least a 70 meter. And then bumping that up to the NGVLA, which is, again, one of the next generation radio arrays, 244 arrayed together 18 meter dishes, we're able to significantly improve our downlink performance. And another thing that I would like to mention based on yesterday's talk was, I think it was Alan who pointed out that acquiring the services from the NGVLA is definitely going to be a NASA and NRAO coming together type of effort. And Joe Smith also mentioned that during our NASA HQ presentation. So I would say, aside from pointing, really getting on good terms with the NRAO and especially the NGVLA folks is going to be one of our biggest and most important challenges, and see if we can get away with using their or operating at their facilities. So what are we going to do if one of our RTGs goes out? This was also brought up yesterday, so I'd like to address it briefly. If we do have a failed RTG scenario, then we would operate at a reduced science with a reduced science suite. And in that survival scenario, we would also have to reduce the amount of power that's dedicated to telecoms, as everybody's going to see a reduction in power allocation most likely. And because we're going to drop from 90 watts being fed into our TWTAs to only 25 watts, that really gets out of the sweet spot or the range that the TWTAs, or the traveling wave tube amplifiers, are designed to operate at. And so at these lower power levels, we don't get quite as efficient of output. So here we're demonstrating on the dashed lines that with a failed RTG, these are the performances that we would see. And luckily at our 50-year mark of a 375 AU with a failed RTG, if we in fact are able to use the NGVLA, then we can still almost get to that 500 bit per second goal that we have. So not all hope will be lost. So in terms of mass reduction, obviously we're gonna have this honkin' 5-meter dish on our spacecraft. So with that, we're gonna have a pretty heavy telecom system. Assuming a legacy design following the same composite dish that New Horizons used, if we scale that up, or New Horizons and Europa Clipper, if we scale that up to a 5-meter dish, that's going to be roughly between 50 and 65 kilograms for just the reflector. So that's really the big hitter that we need to focus on. And in terms of mass reduction, there are a few other alternatives to a solid composite reflector that we can look at. So we talked to a few different vendors, and the most reliable non-deployable version that we found was from L3 Harris, and they call it their fixed mesh reflector, FMR for short. And you can see in terms of aerial density, it's almost half the aerial density of the traditional solid composite dish that we've been using. And then in terms of a trade study, if you look to the plot on the left, the main takeaway is going to be that the blue lines, the blue solid line shows the data rate and performance for a solid dish, where the blue dashed line is the performance for a fixed mesh reflector. And you can see that they're almost identical. Whereas when you look at the orange lines for the solid and dashed lines, they represent the solid and fixed mesh reflectors respectively. And you can see that although the performance is almost identical, and that's because the surface error that you see for an incident wave at X-band is really pretty negligible in this case, or they have really minimal surface error, we keep that high level of performance and high level of efficiency, but we're able to reduce our mass considerably, especially when it comes to using an enlarged 5-meter dish. And to the right in the table, you can see this in quantitative format where the data rates are nearly identical, but the mass is reduced by almost 20 kilograms. And in terms of a swap unit that we arbitrarily came up with, BPS, or bits per second divided by kilogram, we really get more bang per buck when we go with this fixed mesh reflector approach. And again, we surveyed a lot of different reflectors. Only one other alternative that we surveyed is shown here just because I thought it was really cool. And I believe DirecTV and HughesSat satellites for their MSat-1 and MSat-2 satellites use these types of springback or membrane reflectors. But ultimately, we didn't consider these because they weren't thermally appropriate for what we were looking for. But the fixed mesh reflector has a high level of emissivity and really can be swapped almost in without any problems for our solid composite reflector. So, pointing. The whole challenge with this very, very deep space communication link. Our current pointing scheme, I stole this data from Gabe Rogers. So if I don't do a good enough job explaining it, perhaps we can talk about it further in the discussions. We have a spin stabilized spacecraft. Possibly it will become dual mode where it'll alternate between 3-axis capability and spin axis capability or spin axis stabilization. And due to longevity and reliability concerns, we're really not reliant on using any type of reaction or momentum wheel in our design as most traditional 3-axis stabilized. Sorry, I'm getting a little feedback. Most 3-axis or conventional pointing mechanisms are used. So we really rely on thrust vector control as Voyager does right now. So at least we have a good bit of heritage in terms of proving out the lifetimes of that pointing technology, and that's what we're relying on right now. So what's shown on the right is the deviation in our initial inertial spin vector from launch through a few years of the mission. And the main takeaway from this is that early on in the mission, if we want to retain our tight 0.2 degree pointing requirement, then we're going to require more precession more often to retain that level of alignment and pointing precision. Later on, that view of Earth gets a little bit better in terms of how much it deviates relative to our inertial spin vector. And again, this is all the fun and games that comes with having a spinner as opposed to 3-axis stabilized spacecraft.
Reza?
Yeah.
Just to clarify, that's degrees per day. So in 2041, it's moving over 0.2 degrees per day.
Gotcha. All right. Thanks for clarifying. Okay. So if we want to improve on that pointing capability, what do we need to do? Well, we surveyed a few of the technologies that are being brought up right now. Obviously, the benefits to using electronic beam steering or electronic pointing is that there's no moving parts. So in terms of long-term reliability, that seems more favorable. There are a few options when it comes to this. There's complex feeds or multi-beam feeds that array together at the feed, and that provides some level of steering. The downside to that is the level of efficiency goes down as you introduce more feeds, or more horns into this complex feed. And really for higher level of pointing accuracy, you need more feeds. So that's really a whole nother trade to look at for that specific technology. Then there's the case of using a digitized metasurface, which is really, really useful, but unfortunately it's only limited up to about L-band. When you start getting at higher frequencies, the phase precision of the capacitive elements that's usually used to adjust the phase of each one of these pixels really drops off a good bit, and they become pretty unreliable for anything above, I would say, 8 gigahertz or 4 gigahertz. And then there's another neat survey that provided an outlook at a lot of different tunable metasurfaces. And really the takeaway from this is that there's only a few that are viable for tuning in our gigahertz range that we're looking at. So future investigations would likely need to focus on more of these phase transition or MEMS type devices for adjusting our beam steering. And the very bottom down here, as I mentioned before, and I glossed over, is the capacitive tuning, and that really doesn't have quite the level of phase accuracy that we're looking at. So that's electronic pointing, and that's as much as I'm going to dive into that. We can talk about it further in the discussions. There is also the alternative of a mechanical pointing mechanism, which most people are familiar with, uses actuation. So what type of technologies could we use for that? We had kind of an Occam's razor type approach where we did a quick simulation using a tip tilt subreflector. So in our design, as I showed earlier, we have our primary reflector, and then we have our subreflector / MGA. It's dual purpose. And we looked at if we could tip and tilt the subreflector, what kind of pointing accuracies we could achieve. And this actually seems pretty viable. The only challenges really are if we do use an actuator for this type of approach or this type of pointing, then what kind of actuators can we use? Because obviously the lifetime is an issue. So digging deeper into that, in 1984, a German company by the name of Dornier, then renamed and acquired by DSA, then EADS, now known as Astrium. So a lot of little Russian doll type acquisitions going on there. They came up with a pointing mechanism that steered or tipped and tilted the subreflector as we were talking about. And they were able to reduce their pointing error from almost exactly where we were at with 0.2 degrees down to 0.03 degrees. So that got us excited. Unfortunately, we found out that because of the mass of the reflector, they never launched this bad boy or this communication satellite. So it was left just sitting in their archives. And that used just conventional motors. So that was not very appealing to us. But on the plus side, after talking to some colleagues at JPL, they mentioned that Hubble actually has been using an electrostrictive actuator, which is very similar to piezoelectric actuators. And the pickoff mirror that was used to improve the pupil shear that was seen on the Hubble Space Telescopes, that pickoff mirror used these electrostrictive actuators, and it's actually been installed on Hubble since 1993. So it has 27 years of working operational legacy. And in fact, this technology seems so encouraging that Northrop Grumman took over Genetics, the company that developed the technology, and all of these actuators, these electrostrictive actuators, actually hundreds of thousands of them, are now being used for the deformable mirror technology on the W1 Space Telescope. So there's actually some legacy that we might be able to pull the strings on and kind of chase further if we really want to improve on our baseline X-band design. So that leads into X-band versus higher frequencies and hopefully higher data rates and what that would look like. So if we were able to recreate the success that was seen from the Dornier communication satellite, which they had a 4.7 meter dish, we have a 5 meter dish, so it's pretty darn comparable. If we were able to reduce our pointing error from 0.2 degrees to 0.03 degrees, then that puts Ka-band on the table for us. And on the left, you can see our X-band performance, which we already showed slightly before on the swap optimization slide. And if you compare that to the different size dishes that we would use or that we could use for Ka-band, then if you just look at the data rates, it's almost a factor of 4 improvement in terms of downlink performance. So that's assuming that we keep the same size dish. So in the later slides, I'll show or I'll tack onto this, and ultimately, if we are able to use Ka-band, then a mutual decision, at least thus far, has been made amongst the team that we would shrink our dish down so that we would reduce our mass and possibly improve the field of view of some of our instruments, or make that less of a hassle at the very least. So yeah, really Ka-band is something that we want to strive for. It's definitely something that we could push towards. Optical communications is a bit more of a stretch. There have been a few past missions that have suggested it. The Mars laser communications demonstration was developed and it was almost ready to go until the Mars telecommunications orbiter was canceled. So although we have the link models and everything for that, that ultimately never took flight. Psyche, on the other hand, is definitely going to be using at least an optical downlink. I think it's optical uplink as well. It might be hybrid. But both of these technologies, or both of these comm systems, you can see they were designed from pretty reasonable sized, modest laser apertures with lenses in the diameter range of 30 centimeters or 20 centimeters. And they were downlinking to the Palomar Hale telescope. Unfortunately, because our link is so much more difficult, from the distances that we were looking at, if we wanted this communications link to close, then we needed a pretty hefty 1 meter lens for our laser transmitter on board. And that would have to be received by a space-based telescope 3.7 meters in diameter. So this is a little out there. It's definitely the lowest TRL option that we have, and it requires a good bit more of effort. And again, we had to take it out to space because we just couldn't overcome the amount of scattering or atmospheric effects that we encountered when trying to communicate through the atmosphere. And we really even turned all the knobs that we could almost. We assumed very, very tight pointing error, 10 nanoradians. We assumed using a terbium-doped fiber amplifier that gave us a 45% electrical optical efficiency, 50% quantum efficiency detector. That might be the only knob that could improve. New technologies are, we got some assistance from Gloria Jakobovits in AMDS, and she did some background into helping out with a lot of this. And we're even assuming 1 photon count per bit. So we're already really, really spreading ourselves pretty thin in terms of TRL. We tried to make the comms link close with all of these next generation telescopes, ground-based telescopes that are being suggested, as you see down here. That includes the ELT, and we still couldn't get it to close. So we're really looking more so at X-band and Ka-band likely. And kind of summarizing all of that together, this next slide has pictures, so it takes a while to load. You see a visualization of each one of these pointing, or you see a visualization of the detectable flux density levels for each scheme. So what you see is there's a dashed line, and that resembles the 3 dB margin that we allocate to ourselves. And the solid line is 0 margin. So you can really see, as Gabe was mentioning yesterday during the previous comms talk, if there is any sort of anomaly as you move up in frequency, especially at optical, there's really 0 forgiveness. And kind of stepping left to right, you see the different performances, and for each one of the X, K-band, and optical notional designs that we put forth, they have different pointing errors as they require. And I would say another takeaway from this would be that the TRL level, of course, for the leftmost system is pretty much ready to go today. If we were going to launch, we could put that together pretty soon. It's all using high current state-of-the-art technologies that have been flown. I would also like to mention that the performance that you see for the Ka-band, it's using a 2.28 meter dish as opposed to a 5 meter dish. So we shrunk down and took away some data rate from ourselves in order to make the size of the dish in the comm system more favorable to the spacecraft as a whole. After all, we're not just flying a comm link up there, we're flying a spacecraft. So with that being said, that's my last slide. So if we would like to open up the floor to any questions or discussion, I'd be happy to take them. Yeah, thanks for listening to me talk.
Great. Thanks, Reza. Some really good stuff here. There's been some interesting conversation going on with chat, and I know you haven't had a chance to keep up with that, given that you've been presenting. So let me just kind of go over and see if we can summarize some of that stuff. So there was some discussion about the SLS fairing and how big it is, whether we could even get something bigger. And Rob Stoke mentioned that there's a potential for a 10-meter fairing. And so the question then becomes, would something like that be useful, given that the fairing itself would be heavier and a dish would be much heavier? What kind of rate increases would we see from a, let's say, a 7-meter dish, which is sort of the peak of your curve there?
Yeah, rule of thumb, I would say, based on the slide that we showed earlier, bumping up from the current 5-meter dish diameter that we have to a 7-meter dish, you would see about a 20% improvement in data rate. So
Okay.
right now, yeah.
And what do you think the mass, I mean, I'm asking you probably an unfair question, but what do you think the mass increase would be?
I would say it would definitely be a pretty significant.
Yeah, probably more than 20% though, right?
And that might make us consider things like larger deployables or something like that, because they tend to have lower aerial density, or lower mass in general with a lot of the new age deployable technologies. But another thing to consider as well is this was a trade not only between the comms team, but also the science instruments and their field of views. So if we make the dish too big, then we might take away from some science.
Right. Yeah, and that was one of the things that also came out in the chat discussion as well. Let's see, Ben Alterman was asking whether there were any sort of hybrid antenna approaches that we could consider, say a 5-meter fixed dish with a deployable out to 7 meters or something like that.
The 5-meter fixed dish with a deployable out to 7 meters?
Yeah, so somehow be able to spring it open to make it a bigger dish once we've got it.
I have not heard of that type of a hybrid system. Most hybrid systems that I've seen, they typically combine either that complex feed that I showed or even a phased array as your primary source with like a metasurface type reflector or some sort of steerable reflector. So not only do you have some sort of steering from your initial feed, but from the reflector as well. Those are the main types of hybrids that I've seen. And I know those are also used by comm satellites in GEO. So.
Okay, so that's something maybe we could consider as we go down the road, but right now we don't think there's a whole lot of something out there in the way of development that we could leverage from. I think is probably the best summary. Okay.
Right.
There were also some questions about atmospheric effects and whether there would be some help by putting the receiver in space.
Yeah, I'm sure that would always help to get rid of atmospheric effects. You would improve your, there would be definitely less sky noise affecting your overall system temperature. It would be hard to get the types of apertures that we need or the size apertures that we need into space. I would say arraying is already pretty difficult on the ground, so arraying in space would also be another challenge, especially whenever it comes to not only the arraying aspect of it, but also just getting like equivalents to DSN size dishes in space.
Yeah, this is an important discussion because this isn't a breakthrough or an invention or some unknown technology that would need to be invented or created to support this mission. This is a technology that we're putting into the unpragmatic bucket based on what we expect NASA to spend money on over the next few decades. Right? So it's not that we couldn't do this. We all know that the engineering and the physics of this works, right? But we don't, as a team, we have said that a space-based relay for this mission, it's not practical to expect that it'll be there for us. And if we try to bank on that kind of investment by NASA, we basically could propose a mission. We could craft a mission concept, I should say, that just isn't executable by the according to the next decadal survey. We just would put ourselves out of the reckoning.
Well, we basically become two missions. The spacecraft that's going out into interstellar space, and then an entire mission that is building then an extremely high aperture space-based
Right.
station.
Yes.
And that's the other thing to consider. We're looking at apertures on the order of 2,500 to 47,000 square meters. These are very big antenna systems.
Yeah, so I
Now,
think
also in the chat is a lot of discussion on optical, where this does start becoming a very attractive idea. And NASA has been looking at a space-based optical receive system in the past. So, and the optical system would help, would be helped considerably more by getting out of the atmosphere.
And tacking on to Michael's comment about that, pragmatism is key. And we tried to keep that in mind. And in this final slide where we kind of showed the buffet of choices, we definitely favor our baseline design, especially because it's a TRL level, it's ready to go. It's TRL 9. Whereas you see the decreasing TRL levels as we go to the right or to higher frequencies, because really the overall complexity for this communication link gets pretty out of hand, especially because space-based elements are required.
Could you remind us, Reza, why the Ka band is TRL 7 here?
Right. So for our X-band design, we're using thrust vector control for pointing our spin stabilized spacecraft. If we want to improve on that and achieve Ka band, we need some form of secondary pointing that, especially for long life applications, as far as we know, it's not ready yet, or it hasn't at least been proven in this application yet.
So this chart is a very interesting one when you start thinking about what would NASA invest in on the optical side, for instance, right? So assuming we can get the next gen VLA, which again is an assumption, at 375 AU, you're talking about 2,600 bits per second. By going to an optical system, you're only going up to about 3,700 bits per second. And so the question then becomes, what would NASA be willing to invest in for an increase like this? And then whether something like this be more useful for NASA across a wider range of missions then really becomes the motivator, right?
Right.
We'll never get NASA, I think, to pay for an optical receiver, based on just our mission alone. So there are things that we would have to coordinate across the community here.
Hey, Jim,
keep in mind,
Mm-hmm.
go ahead, Rob.
I just wanted to say, so one of the other threads, of course, that's running through this, and I see some of it in the chat, is that, of course, anything that you do, it needs to last for 50 years.
Yep.
And that's the problem with the wheels. And my guess is that with a lot of, first deployment on a lot of these optical systems, I think there may be a real question on lifetime, because you have to have some active elements. And so, again, I think that's a thread. The 50-year business is a thread that people are not used to thinking about, but it really impacts this.
Yeah, I know that ring laser gyros have a lifetime of about 2 years. So, the lasers in them degrade over time. So any optical system might have the same thing. It degrades over time.
Right, and we saw some of that with the performance of lasers on ICESat, of course.
Yep. And so one of the things that folks are chatting about again is the idea that there may be some assets on the moon that can help us out sometime in the future, right? So Reza, Dave, have you looked at what NASA's plans are for Artemis and human exploration to see if there's anything there that we might be able to tap into?
As far as I know, go ahead.
Okay, I'm going. I have, in what I have seen in Artemis, I've not seen anything specifically addressing a lunar optical terminal that would be applicable here for deep space. There's considerable interest in SCAN for optical technologies and how they would apply it to Artemis. I think the direction maybe hasn't been quite so clear in the past couple of years, or past year or so. Artemis itself is still pretty young. And a lot of that, though, has been how we are then tying the moon and ultimately Mars back into networking capabilities back to Earth. So there, the emphasis has been more on the higher data rates, higher for primarily, say, trunking links. A lunar-based optical telescope would definitely help. It would be yet another piece that would be hard to fit into a deployed by 2030. Now, optics can benefit here from sort of the same thing that we're saying about the NASA NRAO teaming here, is that you don't need this capability when you launch. You need this capability years after launch. No matter what we do, you're always going to have an RF downlink as well. So you can buy some time there. And if that fits in with NASA planning, then yeah, I think it's, I think at least in terms of that aspect, there's a viable path there. Getting back to Ralph's point, I'm looking at a 10 nanorad pointing requirement, and how are we going to meet that over 50 years? That scares me.
That over any years.
Right. Yeah, I mean that's pushing the envelope of technology now. Yep. One of the things that we're doing in this concept study is we are finding those areas where it really would be helpful if there was continued technology development. Yep. So
I think the other thing that again people are not used to thinking about is if we take the 1000 AU as the aim point, that's about 5 light days out. So that means that trying to do any sort of closed loop tracking over 10 days for a 5-day link back and forth, along with the Earth moving, there's some other interesting problems that typically people have not really thought through.
Yeah.
And yet if you're going to use the system, you'd have to do that. The other thing with respect to the RF, we've talked about this mission around the world at a lot of international conferences, and there's been a lot of chatter about, what sort of an international role might there be or component. And what I've told people is, one way of certainly having very welcome international participation is that other countries and other space organizations currently have and will be building other reception antennas for deep space. And, I'm sure we can provide them with what the frequencies are, and any help we can get on tracking the spacecraft would certainly be welcome. And it's a component that would not be on the critical path for development of anything. And, it would all be to the good for everyone. So it's another thing to think about.
Mm-hmm.
And the only thing I'd like to add to the optical discussion is in terms of it being worth NASA's investment, optical is great, especially for interplanetary links and links out to a few AU like Psyche is currently doing, and possibly even further if they take the same approach that we did, and instead of relying on using the Hale telescope's 5-meter diameter aperture as a receive element, they can scale that up to the next generation of telescopes that are being used as well, if they're willing to share their resources. So the need for a space-based terminal, if it's just these interstellar type missions that are going to pretty extreme distances, these are the only missions that require them, as opposed to the plethora of interplanetary links, then it might be more worth it for them to stick to augmenting the ground-based receive elements, as opposed to developing a space-based one or a space-based telescope for a few links that are necessary, like interstellar probe.
Okay, so Ralph Perez is wondering whether it would be worth looking at a parallel path technology where you've combined an optical with an RF, and then we always have the option to descope the optical later on in the mission if for some reason technology is not developed or just simply doesn't work out. Any thoughts on that?
That's a very good point, actually. And also, one thing you got to think is that regarding TRL of optics is that they are developing incredible technology. They will have to for the Luna to put on the moon, right? And so we could piggyback with that. And their schedule is very aggressive for that. So I think, you know, we're very afraid of TRL and technology, but, you know, they get into incredible progress on the laser communication in space. And we have until 2030 to get there. So I think at least it'd be worthwhile to see all the other technologies available and at least think about, you know, this process.
Yeah. I can see a path to most of the technologies. We still need to take a look at degradations of optics, of the optics themselves on the spacecraft. But you
That's
know,
for sure.
side, I can definitely see a path to that. It's the pointing. It still is a sticker in my mind.
The idea is now at incredible pointing done by some vendors. Obviously, the TRL is still very low, but it's sub 10 nanometers. So.
Yeah. The problem is proving it's going to last. And if it breaks, what do? You know, how do you build? Can you build a one-for-one redundant system for this? What parts are redundant? Do you have a backup RF capability? And if you've done that, have you basically just killed your mass gain?
And that ties on to Ralph Reza's comment about flying your hybrid system, right? So if you're going to fly a hybrid system, then you have to justify the mass if you're going to have to keep the RF link anyways.
Yeah.
Raphael also put a comment in the chat. He says, actually, Raphael, do you want to chime in on this? I like your question a lot.
Well, this is the approach that even the DART mission did, where they have electric propulsion to put a state of the possible of that technology, but they had their normal hydrogen system there. You know, of course, it's a different mission paradigm, but it's the approach that I'm suggesting here, that if it's not mature enough by a certain milestone, it could be easily de-scoped and taken out, you know, of the system. But I think you highlighted that great point, is the mass gains. You know, if you introduce this hybrid system and your RF is already achieving your objectives, then why add this additional complexity? Right. So
well, it does allow you to maybe back off on the objectives that you're assuming that the RF system is going to achieve. You know, maybe the compromise here is an optical downlink paired with a 1 meter dish. So that you have a backup plan, but that backup plan is definitely now de-scoped in its capability. So
I think this is.
There was one question. I'm sorry, go ahead.
I was going to say, I think this is a suggestion we ought to take back to the engineering team and the science team, and let's put a little more thought into this. I think this is one that we ought to consider an action going forward for the concept study.
I'm going to capture that. There was Carrie had an interesting question, Reza, on the use of phased arrays for comms and whether or not that would help us with pointing and steering.
Yeah. So I think somebody else also mentioned the hybrid approach. And as I mentioned, most comm satellites nowadays, they use a combination of some sort of phased array with their reflector. And whether that be an advanced reflector with additional steering or not, that's definitely something that they use, but the level of pointing accuracy that we require, I'm not sure if we can fit that. It would probably require more deep, detailed analysis, whether or not a truly state-of-the-art phased array would perform the way that we need it to. And it might very well end up being that the phased array would be close to the size of our reflector. So it's definitely something that if we decide to pull the thread on, it could have rewards, but we need to look into it more seriously.
Right.
And I don't know, I was just asking because I'm naive on the subject. Are there any savings in mass or power or adaptability? Could you ramp up or down the power you throw in and the bit rate if you needed that with a phased array versus a fixed dish? Or is it independent of that?
if you were to go to a phased array approach, sort of like what we do with radar systems, where you have a phased array that's built of hundreds of transmit receive modules, each driving elements. That's an extremely powerful capability. Combining power in free space is one of the ways, probably I think might be the only way, of being able to combine RF power without also losing RF power. It would require us to
I think the biggest advantage would be the beam forming.
yeah, you get the beam, well, okay, you get beam forming, you can get beam steering out of it. It is for deep space, would this be a lower TRL approach? I mean, a lot of the technologies are really coming together to do this. Because we can build efficient solid state amps. More or less, okay, we're just now getting to the point where X-band solid state is as efficient as a tube. And this is still in the lower power regimes. So there would be a DC power hit probably.
Doesn't that sort of digital electronics have a higher lifetime risk than a tube?
Solid state, we don't. That's a good question. I mean, we have the problem in that, the transistors that I would use here, gallium nitride technology, they just haven't been around long enough.
And the bigger picture question is, the phased array could possibly allow you to steer your beam without steering your spacecraft, or it could get you better pointing. But we have the old tried and true method of steering spacecraft with thrusters and ACS systems. So is it worth going to the phased array for all the mass and power and risk issues?
What it might actually buy you is a combination of the two. So if the spacecraft is getting you relatively close, can you tighten things up then with secondary electronic steering? Now, as Gabe has pointed out, it's a very complex problem. You're dealing with a number of different issues, all contributing to your beam not being on Earth, and having to track all of that out and compensate for it.
Especially on a spinner.
Yep. Yeah, I mean,
it's light minutes to light hours to light days away.
Right.
Feedback loop is slow.
Yep.
Yeah, and in fact, I would very much, if at all possible, try not to do any kind of closed loop here.
Well,
or if you're doing a closed loop, you're basically auto tracking on the uplink.
Mm-hmm. Yeah, I just don't think closed loop is going to be achievable here. I just really don't.
Yeah. Which, by the way, if we had to, that ties you back into the uplink problem. That means that you now need an uplink going.
Mm-hmm. Yep. All right, this has been some really good discussion. Any other comments that we want to raise? Any questions? Any other great ideas? I'll even take lousy ideas at this point.
Excuse me. Let's fly an X-band.
The X-band system really has the advantage that we could just go build it.
Yeah, it really does.
We have all the parts.
Yeah, I think the other big problem is just knowing where the spacecraft is to a precise enough location with respect to the Earth to get the pointing. You need 1 kilometer of knowledge for every billion kilometers that you have for you get down into like the 1 nano, radian range and stuff like that. So it's really, really hard, I know from New Horizons, to know where the spacecraft is in space when you're not near a target. Yeah. We're talking tens of thousands of kilometers. And every time you fire a thruster, you introduce maybe a couple of fractions of a millimeter per second of delta V, which means that it's going to drift off, which means that the positional errors that you need to know to get your angular errors are just going to grow outside of what I think is capable for optics.
And Gabe, that would be a wonderful number to have. If we had perfect capability to point the beam wherever we want to, and we were limited solely by our knowledge of where to point it in the first place, what is that lower limit?
what is the error around our knowledge of where Earth is, basically, from the spacecraft?
So it's tons of a combination of factors. A couple of them are due to just knowing time. New Horizons has a very nice ultra-stable oscillator. So time itself doesn't drift very much over time. But if you don't know the exact precise time on board the spacecraft, then any onboard ephemeruses that you're flying will be off. And when you're traveling at something like, 36 kilometers a second or something like that, 1 second of inaccuracy throws you far enough off that you've totally swamped your pointing accuracies needed for optical. So, it gets really, really complicated really, really quickly. And that's only one small part of the pointing that you have to deal with.
And this extinction by anomalous events when it comes to pointing is definitely something that I think one mutual reason why we're all a lot more hesitant to lean towards the optical scenario or really, really tighter beam widths, especially when you look at the data rates that you can achieve, at least on this final slide. It's not really worth the improvement.
The other concern I have, which is something we're having to deal with New Horizons now, is parallax. So the stars that we're seeing at 50 AU are not the stars that we see at Earth. So the information that we get out of star trackers and other instruments on board have to be compensated for dynamically to basically adjust for the position of the spacecraft now that we're at 50 AU, 100 AU, 500 AU and stuff. So that's something we also have to take into consideration.
All the parallax shifts should be about a factor of 50 worse than they are at the Earth, right?
Yep. Okay, we've got about 5 minutes left in the session, and there was one last comment from Ben that I think is interesting for folks to realize, and that's we have presented an X-band concept, and he points out very validly so that this still relies on NGVLA, which is in development, but very early in development. And so, so no matter which of these choices that you see on this slide, there is some risk involved here, right? So we can build an X-band system, but it still does rely on having some pretty sophisticated ground systems on the other end, right? I think that same statement is true for KA and for optical as well, as we pointed out. One of the reasons, at least in my mind, and maybe Dave and you and Reza can comment on whether this is valid or not, but one of the reasons why in my mind I'm less bothered by the NGVLA issue is because it is on the books already. These other systems are not, right? And so there is some, even though there's some political issues associated with trying to get access to it, and we do have some contacts with that community that are encouraging, there is still some risk here that we're not going to get access when we want to have it. So, we got to recognize that and make sure NASA knows this. But to my mind, it is still the least risky of the ground station paths that we're talking about. Is that?
Yes. And those are the reasons to be pessimistic, but reasons to be optimistic as well are that we showed in the previous slides. We're really not going to really require that transition until almost 200 AU. So
it's actually a little bit closer than that right now operationally. Right now we're assuming that we're transitioning over around 70 AU, but you're still 10 years out. So, and at that point you can also be phasing in capability.
Right.
So yes, it is absolutely a risk. It's absolutely filled with technical issues and political issues and operational issues. At the very least, though, we're moving those issues onto the ground and keeping the spacecraft low risk.
That's a fair point. All right, well, we need to wrap up. It's almost time for a break, and I do have an announcement that I want to make. I understand from Andrea that our website is having issues today, and so if you're counting on the website to find our next sessions, then what I recommend you do is go back to the emails that she's been sending out every day. One of them contains a document that has a list of all of the sessions with all of the links that are needed. And so that's probably a more reliable place to go look for links for the next session.
Jim, can I, since I'm one of the next speakers, can
Yes,
I, is it okay if I advertise in the chat the link for mine?
right ahead.
We can try.
Yes, please.
Yes,
We can
please do,
here
Casey.
to help bootstrap people. That might help.
And then our next session is going to be on the Oberth maneuver. That will start out a little bit with me giving some words about the slides that I presented on Monday about the Oberth maneuver, just to set context. And then we'll have Doug Meehoke talk to us about the materials work that he's been doing to help us understand what a shield design would look like and help us try to figure out what the masses for these things would be as we're going into the next phase of our concept study. So Casey, I didn't see, did you post the link that we were talking about?
I just did.
Oh, there it is. Got it. Okay, so it's just come up now. So please, I'll leave this up for a little bit so you can copy and paste. That is the, right, you're doing the particles, is that right? Astrophysics?
I'm doing astrophysics science.
Yeah, you'll be doing astrophysics, which is the opposite of the solar Oberth case. Okay.
Yeah. The other extreme.
That's right. With that, thanks, Reza. I think this was a really good presentation. It really laid out the issues that we're struggling with, and I'm glad that we had a lot of good, lively discussion about this and some good ideas that we'll go back and consider forward.
Me too. It was a lot of fun.
Yes, it was. And with that, please take a break, and we'll see you in about 10 minutes at the next session, whichever one that will be. All right, I'm going to go ahead and pause and stop the recording here, and then I'll give it a couple minutes, and then I'll go ahead and end the session.